There are 8 countries that have tested nuclear weapons.
The likelihood of any one of these countries using their nuclear weapons in an attack on another country is very small. The real threat as far as nuclear weapons is concerned is with a terrorist organization that could potentially obtain a nuclear weapon. They could do this by either building their own weapon or by stealing a weapon from one of the current stockpiles. This is a primary concern to the United States, as it is the target of many terrorist organizations.
Keeping track of all special nuclear material, that is, material that could be used to make a nuclear weapon, is an arduous task. The amount of plutonium-239 needed to make one weapon is only slightly larger than a baseball. Therefore, it is important that all special nuclear material is accounted for. The most popular way of finding and identifying lost or stolen nuclear material will be to use radiation detectors. Each special nuclear material emits a unique radiation that, if detected, could be used to identify which isotope emitted the radiation. Another difficulty that arises in special nuclear materials detection is the shielding of radiation. If radiation being emitted from a certain material is shielded, then the detectors will be receiving a much lower signal. This makes it harder to identify what type of material is emitting that said radiation. This is a problem because then we'll not be able to determine whether the material is dangerous or not. The Detection for Nuclear Nonproliferation Group at the University of Michigan is testing and optimizing current techniques used to detect special nuclear material such as plutonium and uranium. They are also developing new techniques to detect special nuclear material. Since plutonium and highly enriched uranium can be hard to come by, the group must use computer simulations to test certain detection techniques. The data output from a simulation is compared to data from a real measurement. If possible, the simulation is improved so that the next time it is run, the output is more representative of an actual measurement. When instant radiation is deposited within a scintillator detector, a flash of light is produced. This light is then converted into an electronic pulse. The larger the pulse, the more energy deposited. This summer, I determined how the operation of a liquid scintillator detector was affected by its orientation. Inside each liquid scintillator is a small bubble that changes position when the detector is turned through various angles. This can affect the size and shape of pulses coming out of the detector, which may lead to a misinterpretation of data if it isn't accounted for. Here in the two black cylindrical shapes are liquid scintillators. They are latched onto a device that allows you to change the angle at which the detector is positioned. After connecting the scintillators to a power supply and digitizer, they are ready to take a measurement. The detector is hooked up to a digitizer that digitizes the pulses and inputs them onto a computer for storage. Here you can see the size and shape of the pulses as they are measured. It was found the larger 5 inch by 5 inch liquid scintillator was most effective at a negative 90 degree orientation. The 3 inch by 3 inch liquid scintillator was relatively unaffected by changes in detector orientation. I would like to thank the entire DNNG group and offer special thanks to Professor Sarah Pozzi for giving me this wonderful opportunity, and Eric Miller for providing guidance throughout the summer. Thank you.